Hey guys, welcome back to my channel. So till now we have seen use of linear models, we have seen linear regression, we have seen linear classification, we also saw linear multi-class classification. So we have covered fair bunch of linear models, but now it is time that we move a step ahead and we start talking about deep learning and deep neural networks. So in this video we'll cover the introduction of deep learning. We'll understand why deep learning is needed, why linear functions do not work for certain use cases, what deep learning is or deep neural networks are, what is function approximation, and then we'll also see an example of how using a deep learning model or a nonlinear model can actually help us solve problems that linear models are not able to solve. So let's get started. So let us first start by understanding why linear models do not work, right? So here I have a data set, two data sets. In one we can see easily that using a single line we are able to separate the data into two different classes, right? So this is something that we have been seeing in our previous videos as well, where the data is linearly separable. Now what happens in a use case where that is not the case? For example, here, right here, drawing any linear line, any one linear line will not successfully separate the data into or correctly classify the data into two classes, right? There is no single model that can do it. So here we see that this is basically your limitation of a linear model which is not working. So now what can we do with this, right? So the first thing that we will try or we should try is that, okay, one linear model is not able to solve, but can multiple linear models solve this? If can I have a stacking of linear models, and will that be able to give me an ability to separate out data which is not so simple and such little nuanced data? So the answer to that is no. Even if you stack X number of hundreds or thousands of linear layers together, the end result or the end approximating capacity of that entire system will still be linear. So let us understand why that is the case. So for example, this is your linear model. This is what we have been seeing so far. Now you have another linear layer which basically is like this. So now if we substitute and see the end result, you can substitute it like y1 is equals to y1. You substitute the value of y here, you put like this. So if you expand it further, this is what you get, right? Now what if you can see clearly that this is again a simple linear model and nothing else. So basically even if you stack multiple linear layers, here we see stacking of two layers, the end result is still a linear model. So you basically do not gain capacity of approximating complex functions even by stacking multiple linear layers. So this data set we cannot separate even if we try to use multiple linear models, right? So what do we do? So we need something which is known as non-linearity. So in a very simple term, non-linearity can be defined as a function where the input and output are not proportional to each other, right? So what does that mean? What is an example of a non-linearity? So an example of non-linearity is a ReLU function, rectified linear unit. This is a very famous nonlinear function which has been used in most of the modern deep neural networks and has performed exceptionally well. This is not the only nonlinear function. There are other nonlinear functions like tanh or sigmoid, which we will discuss as and when the use case arises. But in this video, I just wanted to focus on ReLU because this is one of the most optimal and widely used nonlinear function. So what is a ReLU function? ReLU is nothing but a max of x comma 0. So this is a very simple function. It's a very easy to compute function. It's just the maximum value of x and 0. So if you want to plot ReLU on a curve or on a graph, so basically this is your f of x, this is your x. So what ReLU is just this line, right? So when x is less than 0, ReLU is 0, and when x is greater than 0, ReLU is x, right? So this is the simple function. Now looking at this function, it is very difficult to understand how is it possible that such a simple function is able to give us capabilities to solving more complex problems or highly complex problems. But that is the beauty, right? It's a very simple representation, but it is able to work wonders when put in the right configuration. So this is what a non-linearity is. One of the properties that we have of non-linearity is, obviously, first thing is that it should be non-linear, and second is it should be differentiable almost everywhere. So what does almost everywhere mean, right? So there might be a point or two where the function is not differentiable, but for majority of the cases, or for 99.99% of the points, the function should be differentiable. Why do we have this, relaxation that at few points it might not be differentiable? Because deep learning models run multiple iterations, run on a large amount of data. So even if at some points you're not able to calculate the correct differentiation of the function, it is okay. It does not penalize your model a lot. And here that point is basically x equal to 0. Because at this point you do not know which of the condition triggers of maximum function, whether the x condition or the 0 condition. So here the function is said to be non-differentiable, but in deep learning this has very less empirical impact, and you should not worry about this a lot, right? So now let us see how we can solve the XOR problem using a ReLU function, right? So what is XOR? So XOR is a logic gate which is 0 when both the bits are same and is 1 when both the bits are different, right? This is your XOR gate, right? This is your XOR. So XOR, if you see, is it cannot be separated using linear function. So if you observe a little bit, this basically is a XOR function, right? And we have seen that this data set is not linearly separable. You cannot separate it using linear model. So now basically it warrants a use of a non-linear function. So now I'll write down some function equations. These are equations that I have pre-calculated, which how these equations came or whether these are the only equations is not of concern, but we'll see how using these equations, or basically how using a ReLU activation, can actually help us to solve the XOR problem correctly. Okay, so let me first quickly write down the functions. So let me define fx as 2x plus 2 by minus 1, g of x as 3 minus 2x minus 2y, and v of I as 3 minus f minus g, right? So this is your f of x, this is your g of x, this is your max of f of x comma 0, this is your max of g of x comma 0, this is your v of I, which is input, and here you get the output. Okay, so now let us do the iteration and see how using this system of equations and this stacking of layers using a ReLU activation in between can we solve this problem. Okay, so let us take the case of x is 0, y is 0. So here we expect the output to be 0. Okay, so let's start the calculation. F of x in this case is basically f of x in this case is minus 1, g of x in this case is your 3, and then v basically is 3 minus max of minus 1 comma 0 minus max of can say 3 comma 0, right? So here 3 minus max of minus 1 comma 0 is 0 minus max of 3, which is 0. So this is basically what we wanted as the output, right? Now let us solve for a positive use case. So let me separate this out. Okay, so our x here is, maybe let's take 0, y let us take as 1. So our expected output is 1, right? Now let us solve for this. So f of x here becomes 1, g of x here becomes again 1, and then if I calculate v of I, which is 3 minus max of 1 minus 1 comma 0 minus max of 1 comma 0, this is 3 minus 1 minus 1, which is 1, which is what we wanted, right? So you see how introducing a ReLU non-linearity or a ReLU activation is allowing us to solve this data set, or is allowing us to classify this data set correctly, right? So which was not possible using a linear model, right? So this is the beauty of using nonlinearity. Introducing a nonlinear function allows us to approximate functions of arbitrary complexity. Now comes the question, how do I came across with these equations? So this is a set of equations which can be used as an example. There is no hard and fast rule that these are the only equations that work. And when you will practice deep learning or deep neural networks, this is something that the model will itself learn. These relationships and equations is something that model will itself learn. It may not be explicitly expressible like this, but it will be some hidden correlation of variables and parameters that the model will learn and will give you the desired output. Just to show how it works and have a concrete example in place, I use these equations. So we should not pay a lot of attention to how these equations actually came into existence. Okay, so now we have seen that using a ReLU nonlinearity, you can solve a problem which was not possible using a linear model, right? So this is something which is known as universal function approximation. What universal function approximation refers? It refers to the capability of a mathematical model or algorithm to approximate any arbitrary function with arbitrary precision. So this simple model that you're seeing here, right? Given you make this layer as long as needed, this simple set of layers can approximate any function, any continuous function. This set of layers can approximate, right? This is the beauty of how neural networks or how networks with nonlinearities work, right? With this just simple network of 2 layers basically, you can approximate any arbitrary function, arbitrary continuous function. So universal function approximation is a fundamental concept in fields such as machine learning and artificial intelligence. It enables the development of flexible models that can effectively learn and approximate complex functions, right? So it is a very, very important achievement in the field of machine learning, which is universal function approximation, which, as the name suggests, you can approximate any function in the universe of functions. So now let us talk about what we have been waiting for, deep neural networks. So we saw here that how we have stacked a linear. So we saw one case. We saw that if you stack linear layers, the net result of this is a linear layer. So stacking linear layers together has no improvement in the function approximation capability. Whereas as soon as you introduced one nonlinear layer between two linear layers, the approximation capacity or the capability of the network increases. So that is how a deep neural network is actually defined. A deep neural network can be thought of or conceptualized as a network composed of alternating linear and activation layers. That is it. That is what you need to know about deep neural networks. It is a composition of alternating linear and non-linear layers. And as much as you increase this alternating combination, as you increase the size of the neural network, more difficult and more complex the task you can solve, and your model is more and more powerful. Right? That is all about. That is what you should understand about deep neural networks. Deep neural networks can approximate any continuous functions, and as the input passes through more and more input layers, the network can capture and represent intricate patterns and relationships, enabling it to make more accurate predictions or perform complex tasks. So what does that mean? It means that as you stack more and more layers, it is able to find out very, very intricate details in that data set, very, very intricate features of the data set, and is able to learn on that and make accurate predictions or accurate classification. So if you have a dog image, maybe, right? If you have basically a dog image, something like this. So if you pass that image to the model, it will understand where the dog's hands are, where the tail of the dog is, where the face of the dog is, and as more and more layers are added, more finer details the network is able to learn, right? So this is basically what your deep neural network is. In future videos, we'll see how you can build the deep neural networks in PyTorch, or how basically a neural network representation of a deep neural network is. So yeah, one thing I would like to cover here is that this basically is your computation graph representation. of DNN, right? So there is a neural network representation also where you have neurons stacked together and then there is connection going on. That also we'll discuss. But this is a more easy representation to understand in my mind, because basically it tells you what actually is happening, right? There is no point in confusing ourselves by looking at very complex representations. This is a very simple representation, and this is what you need to understand about neural networks, that it is just an alternation of linear and activation layers, right? So in next video we'll talk more about activation functions and output representations and all those things in upcoming videos. This was just a starting or an introduction to deep learning. I hope you liked this video. Thank you so much for watching. Please do not forget to like, share and subscribe, and now the future videos will be much more interesting, so do press that bell notification icon so that you get notified as and when that video is uploaded. Thank you so much.